a cyclic quadrilateral.
Are we gonna do riddles after this?
Oh, these are the riddles. You mean the harder ones? Yeah.
Yeah,
After this one, we're gonna do the riddles. Or do you want to
Okay.
go straight to the riddles, or do you want to do this first? We go to a riddle. It sounds like you want a riddle. Okay.
Okay, let's do the riddle.
All right. So, yeah, it's so funny how they call it that, like middle riddle. So this one I tried with Simon before, but we couldn't figure it out. So let's see if you guys have an idea. This is a different one, not the one I showed last session.
Is this the one with the Brocard's theorem you mentioned?
This is not the one with Brocard's theorem. This is another one that we tried that we couldn't figure out. And it's kind of the same idea where you could choose any points on A, B, and AC, but it's a different problem. So this should be E, and this should be F. So yeah, really you can choose any points E and F, and then they intersect at X. And then we take the midpoint of B, C, and EF. Yeah, maybe this is related to that problem. I don't know, but it's not the same problem. So we take the midpoints of B, C, and EF, and we call it M and N. And AM intersects EF at Q. And AN intersects BC at P. So AEF almost looks isosceles, so I'm going to try to fix that. So this should be Q, and this should be P. And we want to show AX is parallel to PQ. All right, let's make it look a little better. Make this look less isosceles. So yeah, maybe something like that. Now X almost looks like the orthocenter. So yeah, you can't get everything perfect, but I kind of like that. So yeah, it looks like a simple problem, doesn't it? But yeah, I don't want BFEC to look like it's cyclic. Let's see. Does BFEC look cyclic? Not quite, but I want to make it even less cyclic. So, but now AX looks perpendicular. Yeah, you can't get everything you want. I think that looks good. But now ABC looks isosceles. That should be good. It looks false. Let's see. I'm going to draw AX. Looks true here. I think it's true. Yeah, it looks true to me. So yeah, check your diagram. See, But yeah, I don't think this is a parallelogram, right? I think they're just parallel. Yeah, it's okay. Yeah, I think it's unlikely that these would be a parallelogram. Yeah, it's not a parallelogram. So yeah, I don't know if it's worth letting AX meet BC at a point. Yeah, this one almost feels like it should be like an easy. This is another one of those where it feels like it should be easy, but yeah, we'll see. I'll be right back. All right, I'm back. Yeah, I'd like to thank the person that created this Discord, but yeah, I don't know anything about them. I don't know their name or yeah. They're just this mysterious, smart person with lots of good geometry problems. All right. So yeah, it's a very like symmetric problem. AM intersects EF at Q, AN intersects BC at P. Yeah, I wanted to use projective geometry. But I mean, one way we could try to show it. So the thing is, we could try to show AF, like we could try to show the cross ratio of AF, AX, AN, AE is AF, AB, AD, AP, AC, but that would kind of be ignoring point Q. So MN, yeah, so Simon and I actually noticed that. Yeah, so MN passes through the midpoint of AX. That is true. Yeah, but I forgot about that. So yeah, thanks for bringing that up. You have a Gauss line there. So AQ over AM, maybe we could try to show it's DP over PM. Yeah. So yeah, I find that I like that idea that we used in the last two problems where you have like a harmonic quadrilateral and then you have a point that's on one of the diagonals but not the other diagonal. And then you project everything through that point and you get another harmonic quadrilateral. I feel like that's a really useful tip. So yeah. So we have AF, AX, AN, AE. Yeah, I don't know if this is just about doing the right kind of projection or something. I don't know if it's worth drawing this point. Yeah, we have lots and lots of cross ratios here, right? So we have BPMC is FNQE, and we have BPMC is FNQE. But yeah, we want to like incorporate V and H somehow. So we want to show FH. I'm not sure how we would do this. Let me check the chat. NQMP is cyclic. Is it? I am not sure. No. Because it would only be cyclic, I think, if EF was anti-parallel to BC, but we don't know that. Yeah, I think if AEF was similar to ACB, then that would be true, but yeah, it's not necessarily true. Right? Doesn't it feel like there has to be a way to just like crush this problem with ratios? Like it feels like if you throw enough ratios, it has to be solvable. I just don't know how. Or if there's a better way. Let's see. We want to show AX is parallel to PQ. We try to project through P, so AQM and one of these maybe. So what if we project AQM onto EF? Is there some other point? AQM. Oh, we'd want to project it through P onto AB. So A stays at A. Q should go to the point at infinity. M should go to D. Is there one other point we can do? Yeah, maybe I made it more confusing by adding all these points. I don't know. But so yeah, how would I find AQ over QM? Is there some kind of cross ratio? I want to add in like this point or something.
Intersect PX with EF.
Okay. PX. All right.
Now the problem is equivalent to showing that GI and OX intersect on BC.
GI and OX. Okay. What is
By
O?
two projections of points. QX.
Oh, sorry. Okay. So we want to show GI and QX intersect on BC. Interesting. So if that in that case, we can hide a couple things. Okay, so after a couple of projections, we want to show GI and QX intersect on BC. That's what you're saying. Wait, how is G defined? Is it just the intersection of, I forgot.
The midpoint of AX.
Oh, that's right. Do P, E, C, N, and A, M concur? No, it's close, but not necessarily. So yeah, I kind of like this because we use the Gauss line. Okay, so we want to show that those concur. GI, QX, and BC. Is there any way to use like the SARGs? Yeah, I wonder if we can use this arg somehow.
Intersect XM and XN with EF and BC.
XM and XN. EF and BC.
Now JI passes through A.
Is it equivalent? Is it equivalent to showing that the problem, or you know that's true?
Doesn't look too hard to prove, since actually intersect XQ also with BC
Okay.
to like keep the symmetry. Okay, we basically have that cross ratios BCLJ is equal to cross ratio EFIK.
Well, it would be EFQN when we project through X, but are you saying that you could prove that it's EFIK?
Yeah. Because BP over PC is EQ over QF.
Okay.
Or basically because EFQN is EFQN is CBMP. Those two cross ratios are equal.
Okay.
And like you project another time. But is this enough to show that KL and the JI pass through A?
I'm not sure. Let's see. So J, X, and N. And L, X, and Q. Okay, so do you think the problem is equivalent to showing that these pass through A?
Not sure.
That would be interesting. Do you think we need point G?
I think it is important.
Okay. Oh yeah, this is interesting. So GI and L are collinear, AI and J are collinear, and AK and J are collinear. That's a lot of collinearities. Interesting.
Can we also use Stockless theorem here?
Pappus's?
Mm-hmm.
It could be useful because yeah, we have so many points. We would want. What do you think about that? Yeah, I'm not sure. Maybe we could. All right, so we're about halfway through. It's about 10:30.
Proving that, for example, A, K, and L are collinear, that is equivalent to showing that cross ratio BCLP is FEKN.
But that's just projecting through, you could get that just by projecting through X, right?
Maybe, yeah.
Okay.
So FEKN projecting through X, that is equal to EFNK projecting BCLM, JM.
Okay, so it's a slightly different cross ratio.
Yeah, BCLP is BCJM.
Okay. So if we could show those cross ratios are equal, then that would show that they pass through A.
Yeah. And if we show one passes through A, then the other also passes. Like, I think
Okay.
that's true because we have the same cross ratio.
All right. Okay, so BCLP. Yeah, there's so many. It's interesting. Second. Oh, wait. All these cross ratios make me dizzy. Let's see. So we want to show GI and L are collinear. Q. So basically, yeah, maybe we can use phantom points. Basically, if we let AM intersected at Q, and then we let AX intersected at K, and we let AK intersect BC at L, and we want to show that QX and L are collinear. That's interesting. And and I think that might be, actually, I think it might be kind of, it might be obvious that AK and L are collinear, because we want to show that FKQE is equal to BLMC, right? Wait. Yeah, is it just obvious by projecting through X that AK and L have to be collinear? because like I think this might be just true in general. Like, let's see. Like, I don't even think it matters. Okay, yeah, so I don't even think we need midpoints necessarily. Guess what I'm saying is, if you have something like this, let's say, and you project these points through this, then I wonder if the new ones are always collinear. So like, let's say I just do it like this. Then I wonder if these points are just always collinear. Yeah, I mean, basically, yeah, even if you don't have midpoints, like if these are collinear with O, then when you project it through Z, these are also going to be collinear, and that's just using cross ratios. So, yeah, you don't even need midpoints, right? So basically, AK and L are going to be collinear just because A, Q, and M are collinear. Does that make sense?
Yeah, makes sense.
And I wonder if the same is true with A, I, and J. Yeah, because A, N, and P are collinear, so A, I, and J are going to be collinear. Whoops. And so the problem really, and then we could show that G, I, and L are collinear, because I think we can. And I think it's like the exact same argument. Actually, I think that should be doable. I think it might.
I think we need to show that MK, LN, and IX are concurrent for that. Maybe, I don't know.
MK, LN, and
IX. AX.
MK, LN, well, I guess by definition they all concur at X, right?
Sorry, my diagram is just different. In your diagram, MI, LN, and AX.
MI, LN, and AX. And that would help show that GI and L are collinear? That's what you're saying?
I think.
So yeah, basically everything in this diagram so far we know is true. And we want to show G, I, and L are collinear. So let's say G, I, and L were collinear, and then we project through P. Onto AX. And we get GX, this point. And then, yeah, the point of infinity. Yeah. It's just a lot of cross ratios. So I think like originally at one point, did you say that proving AX is parallel to PQ is equivalent to showing G, I, and L? Well, didn't you say you showed it was equivalent?
Yeah. It is equivalent, and I just proved I solved the problem just now.
Okay.
So you will need to add in 2 more points. Intersection of EF and BC and AX and BC.
Okay.
Like completing the quadrilateral.
Yeah. So here's AX and BC, and then EF and BC.
And now the rest of proof will be like third 3 projections.
Okay.
Okay, so cross ratio LM OD is -1 because
They concur, yeah. L, Q, M, K, and A, B concur. So LMOD is 1.
LMOD is 1.
Or -1. Yeah.
-1, yeah, the harmonic.
Yeah.
So we project through A onto EF, and we get that KQ O and
this point.
Yeah, that intersection point is -1.
Okay.
Then we similarly have that JPOD is -1.
Okay. So IRNO would be -1.
Yeah. So we actually didn't need to project the last one on EF, but doesn't matter. But we have to project. So JPOD projecting through A on EF is INOR.
Right.
And projecting through G onto BC, INOR becomes let's say L, but we want to show it is L. So L M OD.
Okay.
And basically, this is proven because we will say like the intersection of GI and BC, but this will be -1, and we already have that LM You don't need the phantom point. You
Okay.
can just like, yeah. So it will be LMOD is -1. We already have that. And we have that when we project through G, cross ratio INOR. We project through G and we also get -1. So G, I, and L are collinear.
Okay. So basically you're saying like, okay, so because INKR is harmonic, then and OLDM is harmonic, then GI and L have to be collinear, is kind of what you're saying, right?
Yeah.
Okay. So then we know GI and L are collinear. And then
you can write this part, or I can actually just write the both cross ratio like projections.
okay.
In the chat.
So really we don't need do we need point K?
Yeah, it is important that we have collinearities like AKL and AIJ.
Okay.
That is important.
All right. Okay, so we could show that G, I, and L are collinear. And then once we know that, then how do we finish it?
Let me remember. I had another projection chase.
That's all right. So yeah, I'm going to start typing this up, what you said so far. So I'll say label the points as shown. Okay, so first, yeah, I'm going to hide these two. And then I'll say label the points as shown. There's too many to type them all out. So projecting through X, we have FKQE is FLMC. FKQE is going to be CB or CMLB. And we can rewrite that as, because you can swap things around. There's 24 permutations, but that should be the same as BLMC. And that implies that A, K, and L are collinear. And then similarly, A, I, and J are collinear. And then by the Gauss line, G, N, and M are collinear. Yeah, I feel like we have to use somewhere that G is the midpoint of AX. And then we have O. So yeah, I'm gonna just have to draw on these lines for 1 second. But we have OIRN is harmonic because, so a OJBP is harmonic. So I'll say T is harmonic, implies that ORIN is harmonic. That's projecting through A. And so yeah, and then, so if we project through G, we get OLM. So OLMB is harmonic. ODLM is harmonic. And then if we project these last two through G, so projecting through G, then we get G, I, and L are collinear. Okay. Zach, I'll be right back. All right. So let's see. How do we show AX is parallel to PQ?
Maybe it is not enough.
Oh, really?
Maybe, I don't know.
Okay. But yeah, like you said, you saw it at one point, so I feel like you must have seen something. But
I mean, I know what I was doing. I was like projecting AX G infinity through P onto EF.
okay.
But then I projected it again through G, but maybe I made some mistake. I think I did something like that.
Okay. So AXG infinity is harmonic, and then you try to project through P. I kind of like that idea. Yeah, we could also project through M, right? Well, yeah, I don't know if that's as good, but then we get K and Q. Oh, but we want to use the parallel. So if they're parallel, then that means that Q, yeah, we'd have to draw GP intersect this. So Q, that point, N and I would be harmonic. And then projecting through A, that would mean J. Oh yeah, that would be kind of tricky because yeah, we'd have to draw another point in. I like that idea though. So A G X infinity. So yeah, basically you have this point and you want to show that QS N, we want to show that QSNI is harmonic. And then we could try projecting those through G. So we'd get M, L, P, then we'd have like a point way out there. So yeah. We want to show QSNI is harmonic. And we could try to project through X. So that's the same as showing that L, oh, but S, yeah, that's a problem. Yeah, I don't know if we want to create point S. All right. What if we project through point Q? So yeah, I almost want to project through Q onto BC. So A, G, and X. A goes to M, X goes to L. So M, L, P, and then there would be a point like far away. And we'd want to show that those are harmonic. So I think that's the same as showing that, let me think about this. So QX intersects BC at L. So we have a triangle AML. And QX meets at L. QA intersects at M. LMP. You want to show LMP and that point are harmonic. Let me think about this. P. So I wonder, that seems kind of weird to me. So we have triangle AML. Yeah, it's the same as saying that GQ and this line meet on BC, although I don't, yeah, that's not very helpful. Because yeah, what is that? It's not very useful. Okay. We could try, yeah, projecting through N, but so we get PM, PML, and this point are harmonic. Yeah, maybe that would help. So let's say I draw the parallel through N to AX. Then if we project AGX infinity, we have PMLS is harmonic. And if we project through Q, we want to show that ML P I'm getting confused. This one looks tricky. All right, let's work on it like another 10 minutes. See what you guys, if we get somewhere, I'll keep working on it, but yeah, otherwise I'll try something new. Yeah, we have a little, about 40 minutes left.
Drawing the parallel through N.
The parallel through N to AD.
Yeah.
Okay.
Then intersected with BC.
Okay.
Okay, now we have that LPSM is harmonic.
Okay.
And then we project through A and get IN, intersection of AS and EF, and Q is harmonic.
Okay.
However, that intersection point should be on GP. So we have like equivalent to concurrence.
Okay, we want to show GT and P are collinear, basically.
Yeah.
So if GT and P are collinear, so if we have IR, that would mean IRTN, the cross ratio would be LDPM. But if you take LDPM and you project through X, whoops. LX goes to Q. So we want to show IRTN is equal to, yeah, it's just getting that T. That's the tricky thing. It seems crazy that a problem this simple would involve all this, but maybe it does. I don't know.
Let's go to the next problem.
All right. So yeah, I could do the middle riddle, or I could try a harder riddle. What do you think?
I would want a riddle, but not with a million cross ratios.
Okay. This one has a lot of mixed linears. So this one, I'll try this one. So I don't think this should be too many cross ratios. So,
oh, I worked on this problem a bit before.
Oh, really? Did you solve it?
Not fully.
Okay. We could try another one then, or it's up to you. Oh, this one I had an idea. This was the one we did last session, but this one's actually, you know what? I kind of like this one. It has a lot of mixed linears though, but I mean, you're trying to prove what you're trying to prove is kind of simple, but I don't know if that really means it's as easy as it looks, because I don't know who came up with this Discord, but they're very good at finding problems that look like they're easy, but they're not. So let's see. So we want to draw the B and C mixed linear in circle. What's the best way to do this? I'll just draw the angle bisectors and then draw the in circle. Okay, so here's the in center, and yeah, really, actually, now you know what? I'm going to do it like this. So that's the in center, but actually, you know what? I'll just do it the normal way. Trying to be creative, but it's not always the best. This should be I. So I want to draw the perpendiculars to these two. Okay. And then basically this is going to be the center. Okay, so this is one of the mixed linear in circles. Let me hide everything I did. And whoops. Then I'm going to draw the other one. I think this is the fastest way I've seen to draw the mixed linear in circles. Okay, so we have both of those. And okay, so F, so we have the B circle with, okay, so this should be F. And P and Q, hey, that didn't work. F. Why won't it be F? There we go. And then we draw CB and CA. So this should be P. And this should be Q. And then we draw the circumcircle of FQC. What is L? I'm going to hide this for now. Hide this. I'll leave the encircle there. But so then we draw the circumcircle of FQC. It meets BC at K. And we want to show BP equals CK. So FI meets, so this should be the midpoint of arc ABC. I don't know if that's that helpful, but it's usually good to draw that. So yeah, this is from my video on mixed linear in circles. If you haven't seen it. So BP yeah, I'm just going to get rid of this for now. What do you guys think about this problem? You want to keep working on it, or I know we just started it, but what do you guys think about like mixed linear problems like this?
This one looks hard.
It looks hard. Okay. You want to try like a different one? The middle riddle? You want to try this one? Let's just.
Don't know.
It might be too easy. We only have 40 minutes left. Let's see if we can solve this. We only solved two of the problems. It's having trouble maximizing it.
Oh, I actually solved this problem before.
Oh, really?
Yeah, I just looked at it.
You remember how hard it was?
It was pretty easy.
It was easy?
Yeah.
Okay. All right, let's try this one.
I did it in like 2 lines or something.
2 lines?
Yeah, 2-line solution or something.
Oh.
But it was like not detailed.
Okay. So let's try this. So yeah, you could show us what you did so far on this, and then we could see if we could finish it. Oops. H. And M and N are the midpoints of BC and EF. So yeah, MN is perpendicular to EF, since EFEC is cyclic. And AN intersects HM at T. Okay. Let's try to make T a little bit farther away. So like this will be point T. And then we draw the orthocenters of TFB and TEC. And we want to show X, Y, and H are collinear. So all right. Oops. All right, so I think we have the whole diagram. That looks good. AN, oh, I need this. So HM passes through the antipode of A. I don't know if it's worth drawing that or not. So do you remember what progress you made on this?
One thing I think I proved is that when you intersect TX and TY with AB and AC, you will get a cyclic quadrilateral.
Interesting. It almost looks like, oh, well, that's clear, right? Because TX is perpendicular. These are both right angles, right? Oh, but maybe with cyclic with X and Y, maybe?
Yeah, with X and Y.
Okay.
And also I proved that not as a specific point for T, but a variable point on this median. For every point on this median. I think that is true for, yeah.
That's true in general.
And then like, we will need to show that we will have some angles which is nice, like TXY is equal to TIG, and that is TAG, and that is CAM. So TXY is CAM, and so we want to show that TXH is CAM, and it may be true that those two are similar, but I'm not sure. Actually, that is not true. Yeah.
TXH and CAM.
Yeah.
Okay, so we want to show angle TXH equals CAM. Um, yeah.
Also, now I see that then we have that line XYH is perpendicular to AT.
AT. Okay.
Yeah. This median.
So if we could show XH is perpendicular to AT, that would solve it.
Probably.
Could H be the orthocenter of another triangle, like with let's see. If I try this. So H would be the orthocenter of this triangle. Okay, so yeah, we can basically get rid of point Y then. We just want to show XH is perpendicular to AT. So that would simplify the diagram. Yeah, okay. Maybe we could show like xt squared, xa squared minus xt squared. Okay, so x is the orthocenter here. We want to use that. I feel like this might be the most intuitive way to use that fact, but I don't know. So that means if you reflect x over AB, it would lie on this circle.
Let's add the Humpty point.
The Humpty point?
Yeah. Or is it called like that?
All
oh,
right.
not that one. The other one on the circumcircle.
Oh, this one. Okay.
What is it called? I forgot.
The Q point, or the
Yeah, maybe something like that.
like the intersection of this and this.
Yeah. It is probably a lot useful because it lies on HM, and also it is cyclic with ATG.
ATG. Okay. So we want to use it. This is the orthocenter. I guess another way we could use it is we know that xg times tg is fg times gb. Yeah, so basically we want to show that x, h, and this point are collinear, right? X, h, and j.
That is correct.
Yeah, so how do we use that x as the orthocenter? That's the key. I don't know if there's anything special about x prime. Those almost look collinear, but they're not. So if x, let's see, we want to show xh is perpendicular to AT. And we want to use that x as the orthocenter of TFB. Maybe, let's try something. Does BX pass through this point right here? Yeah, it looks like it. I don't know if that's obvious, but it looks like BX passes through this point. So let's see. So BX and K look like they're collinear.
That is actually equivalent to the problem.
Oh, really?
Yeah, by the power of a point.
Okay. So if that's true, we don't even really need x. Yeah, I'm just thinking of ways we can simplify the problem. We just need to show that if we define k that way, then we want to show bk is perpendicular to tf. Or we could drop an or we could drop the altitude, and then we want to show what lies on that. So we could try to show IFKE is cyclic, or IAKH is cyclic, or something. All right, we got 20 minutes left. Sir Dar must have popped off. Yeah, because we know that this is perpendicular here, TG. Okay, so it's equivalent to showing that K lies on this circle. You want to go over your solution to the middle riddle?
I mean, you can find it on the server.
Or what?
You can find it on the server.
Okay. All right.
I wrote it there.
Okay. I'll continue with this one. I almost feel like this looks a little awkward. Like I feel like I want to extend BK to like meet the circle or something. And I wonder if there's something special about this point or I don't think those are actually collinear. But yeah, we want to show that if you drop an altitude that it lies on this circle with diameter AH, right? Yeah, I wonder if there's a way to like use the radical axis theorem where like three different things concur at point T. So FK, see this circle, that circle. And this, yeah. Oh, wait a sec. Okay. Yeah, these are hard. Yeah, we solved two problems in the first like almost an hour. So it was like, hey, maybe we're gonna go too fast today, but ended up being really hard in the end. Yeah. All right. So I had an idea with, the problem we solved last time. I'm sorry, the problem we worked on last time where we wanted to show like the perpendicularity. I had an idea for that I think might be very close to working. Do you want to look at that? Or you want to keep working on this until the end?
I really don't know.
Okay.
You can try it. I mean, I wasn't really working a lot on it, so probably won't be very useful.
So yeah, let's see. So it's this problem, and we want to show IJ is perpendicular to DE. So yeah, D and E can be wherever they want. I don't know if we stated the problem with these exact same letters, but yeah, you want to show that IJ is perpendicular to DE. And what I was thinking, so the way we try to do it was we let BH and AC intersect, and we let CH and AB intersect. And we wanted to show that this was parallel to DE. That would be equivalent to the problem by Ricard's theorem. So IJ is perpendicular to DE is equivalent to saying KL is parallel to DE. So what I was thinking of doing was I would draw the parallel to DE through K, and I would let it intersect this at L prime. And then what I would try to do, so actually, let's go back. So here's kind of my idea. So let me draw like a parallelogram here. Basically, so by Pappus, these would concur. And then I would have this, and then these would all be collinear. And also, I think EP would be parallel to BK, and BP would be parallel. Yeah. So I'm gonna hide a couple things here, but so BHK, CHL. So if the problem were true, we'd have a whole bunch of stuff. We would have basically, I was trying to use phantom points. So like the way the problem the way the problem was defined, we let F be the intersection of these circles. But I was thinking, what if we tried to instead like assume this is parallel, and then we'd have like a homothety about point O takes like, it takes H to P, like we'd have a whole bunch of stuff. And then I wanted to show that this would lie on this circle. So yeah, I guess if the problem were true, there would be a lot of stuff that would be true. Like, so yeah, originally we wanted to prove that LK is parallel to DE. But if it were true, then that would like confirm that F light on this circle. So I can kind of show the converse. I can basically show the converse of it, but I can't show the forward direction. I can show if LK is parallel to DE, then if you created all these points and you intersect it with a circle, then I can show that this is cyclic, but I can't show the other way. Actually, I might have an idea here. So let's say we have points A, B, C, D, and E. Is there always a unique point H on this arc such that when you intersect the two like this, then LK is parallel to DE? So basically, if we have a triangle, let's say we have a triangle, because I think that would solve it then. If you have a triangle and you have like any random segment, it doesn't matter. But is there always a unique point on this arc such that when you do this, sorry, like when you complete the quadrilateral, that the long side would be parallel to TU? So, sorry. I think it should be true because like, in other words, as we move V around, the slope of this changes. So yeah, I think, yeah, because the slope of TU is somewhere between the slope of WS and the slope of RZ, right? And when you move V all the way here, the slope would be that. And if you move V all the way here, the slope would be that. So there has to be some point in between where the slopes would match. And I think if I use that fact, I could solve this problem.
So we're using like Borsa-Coulomb theorem or something.
Using what theorem?
I think it is some theorem in topology.
Oh, really? Okay. The
Yeah,
Boris-Ulam theorem?
Or Ulan. I don't know topology. I just saw it on YouTube.
Yeah. So I think what I could do is I could let H prime be the point on this arc such that this slope is equal to this slope. And then I could complete the rest of the diagram. But then I would basically define F prime to be the intersection of this line with the circle. And then I think it would be easy to show that this is cyclic, A F prime EB. So, and then once I do that, once I show that that's cyclic, then that would mean H prime equals H. And I think that would solve the problem. But yeah, maybe I can make a video on it. Yeah, I don't know if it has to be this hard. Actually, I don't even know if you need point M really. But yeah, that was my idea. Okay. All right, so yeah, maybe I'll do a video on that or something. Yeah, we have 2 minutes left, so we could just work on this for the last 2 minutes. All right. All right, I think I'm gonna stop here. So thanks everyone for participating in the session. Yeah, it's been a lot of fun, and yeah, we had some really cool solutions to those first two problems. They got a lot harder than I thought, but yeah, maybe we'll solve them after the session. So yeah, thanks for joining. Leia, I know this is your first time, but yeah, if you have any questions, feel free to post them in the chat. For everyone watching, if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day. Oh, whoops, I forgot to stop the recording.